There is a star called S2. For the last 26,000 years, that star has been falling toward a black hole, not crashing into it, not escaping it, just falling. Every 16 years, S2 swings around the supermassive black hole at the center of our galaxy, Sagittarius A star. At the closest point in its orbit, the star accelerates to 7,650 kilometers per second. That is 2.55% of the speed of light. Numbers like that are difficult to imagine. So here is what that speed actually means. At that velocity, S2 could travel from the surface of Earth to the moon in just 52 seconds. Before you finish the next minute of this video, that star would have moved farther than the distance between our planet and the moon. Scientists have been watching this star complete its orbit since 1992. Two independent research teams working on opposite sides of the planet, using different telescopes, different instruments, and different analytical methods, tracked it continuously for 30 years. The measurements produced by 3 decades of that watching were precise enough to confirm general relativity at a proximity to a supermassive black hole that no previous test had reached. The Nobel Prize in Physics in 2020 was awarded in part for those measurements. But hidden inside that Nobel Prize-winning discovery was something far stranger, something scientists still cannot explain. S2 should not exist where it is. The mechanism that placed a 6-million-year-old star within 4 Neptune distances of a supermassive event horizon is one of the most genuinely unsolved problems in modern galactic astronomy. Scientists have a name for it. They call it the paradox of youth, and it changes what S2 means, not just as a scientific instrument, but as a fact about the environment this black hole has created around itself. To understand what the 30 years of observation produced and what it revealed, you need to understand what the two teams were starting from in 1992 and what they were trying to prove. In 1992, the existence of a supermassive black hole at the center of the Milky Way was strongly suspected, but not confirmed. The evidence for it was indirect. The dynamics of gas near the galactic center, radio emission from a compact source called Sagittarius A star, the velocities of stars in the vicinity inferred from spectroscopic measurements. The case was compelling, but not definitive. To confirm a supermassive black hole by the standards that physics requires, you need to show that a large mass is confined within a small volume, small enough that no known alternative to a black hole could account for it. The way to do that is to track individual stars in the galactic center and measure their orbits. If a star follows a Keplerian orbit, the same kind of elliptical orbit that planets follow around the sun, governed by Newton's laws, with a period and velocity that imply a central mass of millions of solar masses confined within a tiny region, the black hole hypothesis becomes the only viable explanation. In 1992, 2 teams independently began exactly this program. The first was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Garching, Germany, using instruments at the European Southern Observatory in Chile, principally the New Technology Telescope. The second was led by Andrea Ghez at the University of California, Los Angeles, using the Keck Observatory on Mauna Kea in Hawaii. Neither team was aware, at the outset, that the other had begun the same program in the same year. Both were trying to answer the same question: is there actually a supermassive black hole at the galactic center? Both teams were immediately confronted with the same fundamental problem. The galactic center is invisible to ordinary telescopes. 25 magnitudes of dust extinction in visible light make the central parsec, the inner few light years around Sagittarius A star, completely opaque to optical observation. Both teams independently developed infrared imaging techniques to see through this dust. Infrared wavelengths are not blocked by the interstellar dust in the same way that visible light is. Both teams pushed the technology to its limits, developing speckle imaging techniques and later adaptive optic systems that could correct for atmospheric distortion and achieve the angular resolution needed to distinguish individual stars in a region of extraordinary stellar density. Over the following decade, both teams tracked the same stars. Both teams watched the star that would eventually be designated S2 move through its orbit arc by arc. Both teams measured its velocity changing as it moved, accelerating as it approached closest approach, decelerating as it moved outward. In 2002, S2 completed its pericenter passage, and the full orbital solution was fitted to the data. A 16-year ellipse, an eccentricity of 0.884, a semi-major axis of approximately 970 astronomical units, a closest approach of approximately 120 astronomical units. The orbital solution implied a central mass of approximately 4 million solar masses, confined within a region smaller than our solar system. No alternative to a supermassive black hole is physically viable. The black hole was confirmed, not as a probability, not as the most likely explanation. Confirmed by the inescapable mathematics of orbital mechanics applied to 3 decades of direct stellar observation. Genzel described the journey. It took a lot of patience, luck, and always trying hard to get better and better and better. Gez was characteristically direct. There are no other alternatives that we know of. In October 2020, the Nobel Prize in Physics was awarded. Roger Penrose received half the prize for his theoretical proof that black hole singularities are an inevitable consequence of general relativity. Reinhard Genzel and Andrea Ghez shared the other half for the discovery of the supermassive compact object at the galactic center, confirmed through the S-star program. Andrea Ghez became the 4th woman in history to receive the Nobel Prize in Physics. The coverage of the Nobel Prize was thorough on the confirmation. It was not thorough on what the measurements also revealed about the tool of confirmation, about S2 itself. The confirmation of the black hole was the first chapter. The second chapter, the one that produced the most scientifically precise results, required a new instrument. The gravity instrument was a collaboration between the Max Planck Institute for Extraterrestrial Physics and the European Southern Observatory, designed and built specifically to exploit the 2018 pericenter passage of S2, its closest approach to Sagittarius A star in that galactic year. Gravity combined the light from all 4 of the Very Large Telescope's 8.2-meter primary mirrors, separated by up to 130 meters, into a single optical interferometer. The precision of the optical path control required to make this work is described by the instrument's lead designer, Frank Eisenhower, as controlling the path lengths between the 4 telescopes to a precision several hundred times smaller than the thickness of a human hair. Using this instrument during S2's 2018 pericenter passage, the gravity team measured two effects predicted by general relativity that had never previously been measured at a supermassive black hole. The first was gravitational redshift. When light climbs out of a deep gravitational field, its wavelength is stretched toward the red end of the spectrum by the work done against gravity. The magnitude of the stretch is precisely predicted by GR based on the depth of the gravitational potential. The gravity team measured the redshift of S2's light at closest approach and found it consistent with the GR prediction at 5 sigma confidence. The second effect, measured in 2020, was the Schwarzschild precession of S2's orbit. In Newtonian gravity, a two-body orbit is a closed ellipse that repeats exactly. In general relativity, the curvature of spacetime near a massive object causes the orbit to precess, to advance, so that the ellipse itself rotates around the central mass, tracing a rosette pattern over many orbital cycles. The predicted rate of precession for S2's orbit around Sagittarius A star, 12 arc minutes per orbit. The gravity measurement confirmed this precession at 7 sigma confidence. The orbit is not a closed ellipse. It is a rosette. Gez's published assessment of the combined results. Einstein's right, at least for now. However, his theory is definitely showing vulnerability. That phrase, from a Nobel laureate who spent 30 years testing the theory, appeared in the scientific literature and received almost no attention in general coverage. Einstein has passed every test we can currently perform in the gravitational environment of Sagittarius A star. The region where the theory might fail, the innermost regime, between the photon orbit and the event horizon itself, is still below the precision of current instrumentation. The test is not complete. And now, we arrive at the thing the Nobel coverage did not tell you. The star S2 is young. Very young. Only about 6 million years old. This is known from its stellar properties, its surface temperature, its luminosity, its spectral classification, its estimated mass of approximately 14 to 15 solar masses. It is a young, hot, blue-white main sequence B-type star, 6 million years old. That is young in stellar terms. But in the context of the galactic center, 6 million years old is the problem. The tidal field of a supermassive black hole is so intense in the innermost few light years of the galactic center that gas clouds attempting to collapse under their own self-gravity to form protostars are destroyed before the collapse can complete. The near side of the gas cloud is pulled significantly harder than the far side. The differential overcomes the self-gravity of the cloud. The cloud is sheared apart before a protostar can form at its center. Star formation in the innermost parsec around a supermassive black hole is supposed to be essentially impossible. S2 formed 6 million years ago. In the innermost parsec around Sagittarius A star, in the location where it should have been impossible to form, the star that provided the most precise test of general relativity in human history, the star that confirmed beyond reasonable doubt the existence of a supermassive black hole at the center of the Milky Way, the star that won 2 scientists the Nobel Prize. This star exists where it should not exist, and no one knows why. Andrea Ghez named this puzzle the paradox of youth. The question is simple, but the answer has proven extremely difficult. How did these young stars end up in a place where stars should not be able to form? 3 explanations have been proposed. None has been accepted as correct. The first, the S-stars formed further from the galactic center and migrated inward. The objection, the timescale for inward migration is too long for stars as young as S2 to have reached their current orbits. The second, the stars formed in a massive disk of gas that fell into the galactic center rapidly and collapsed during the infall. The objection, no remnant of such a disk has been detected in any observational band. The third, the gas clouds were somehow dense enough to resist tidal disruption. The objection, the density required is orders of magnitude higher than anything observed elsewhere in the galactic center environment. The paradox is genuinely open. The Nobel Prize was awarded for what S2's orbit proved. S2 itself, the instrument of that proof, remains a mystery that 30 years of observation has deepened without resolving. S2 is currently safe. At its present orbital parameters, its closest approach of 120 astronomical units keeps it well outside the tidal disruption radius of Sagittarius A star. The star is not in danger on any immediate timescale. It will continue completing its 16-year orbit for millions of years before any combination of orbital evolution, gravitational perturbation, or stellar mass loss brings it close enough to the event horizon for the outcome to change. But the outcome, when it eventually comes, is not in doubt. The physics that will destroy S2 is the same physics we observed destroying a different star in a different galaxy in real time in 2019. In 2019, a tidal disruption event was observed in a galaxy approximately 215 million light-years away. The event was designated AT2019QIZ. It was observed in real time using the European Southern Observatory's Very Large Telescope, and was tracked from its initial brightening through its peak and subsequent fading over a period of several weeks. A star had passed too close to a supermassive black hole and crossed the tidal disruption radius. The distance at which the tidal gradient of the black hole's gravitational field exceeds the self-gravity of the star. The star could not hold itself together. The near side fell faster than the far side. The stellar material stretched into a long stream of gas along the radial direction, a process called spaghettification, and the debris began falling into the accretion disk. The energy of the infalling material was released as a flare of optical, ultraviolet, and X-ray radiation. The research team described AT2019QIZ as the Rosetta Stones of tidal disruption physics. The first event observed cleanly enough, completely enough, from beginning to end, to fully constrain the theoretical models of the process. What happened to that unnamed star 215 million light-years away is what will happen to S2. Not soon, not in any time frame relevant to any human being who has ever lived or will ever live, but eventually. The orbit is known, the black hole is known, the physics is known, the ending is settled, only the timing is open. We have a vantage point for this event that no observer anywhere in the history of the galaxy has ever had for a tidal disruption. We have been watching S2 since 1992. We know its orbital period, its eccentricity, its semi-major axis, its mass, its surface temperature, its age, its spectral classification. We have confirmed general relativity using its orbit. We have won a Nobel Prize from its orbit. When S2 eventually crosses the tidal disruption radius of Sagittarius A star, it will be the most precisely anticipated, most thoroughly characterized, most carefully monitored stellar destruction in history. And what we are observing when we watch S2 is not what it is doing at this moment. The light travel distance from the galactic center to Earth is 26,000 years. The S2 we see in any telescope tonight is the S2 of 26,000 years ago. The star as it actually exists right now, at this moment, at the actual present instant, is 26,000 years further along in its orbit than what any instrument on Earth can show us. We are watching a recording. The star has already moved on. Here is the question I want to leave in the comments section of this video. We know S2's orbit. We know the physics that will end it. We have watched the same process happen to another star, 215 million light years away. The ending is certain. The timing is not. And everything we observe about S2 is 26,000 years old. The star we track is not where we see it. It has been 26,000 years since any of those photons left the galactic center. The actual star, at the actual present moment, is invisible to us. Does knowing the ending, but not the timing, feel like dread? Or is it the most honest relationship you can have with a thing in the universe, knowing the outcome without knowing the when? Leave your answer below. The most honest responses will be read at the opening of the next episode. 3 things to carry with you from this episode. The orbit of S2 confirmed a supermassive black hole at the center of the Milky Way. The confirmation was precise enough to win the Nobel Prize. The same orbit revealed that S2, the tool of confirmation, should not exist at its current location. 6 million years old, in a region where its formation should have been impossible. No accepted explanation. The orbit confirmed general relativity at the highest precision measurement near a supermassive black hole ever performed. The person who spent 30 years doing this described the result as showing Einstein's theory is definitely showing vulnerability. The region where it might fail is still below the instrument's precision. S2 will eventually cross the tidal disruption radius. The physics is known, the timeline is not. Everything we observe is 26,000 years old. If you want the science without the softening, subscribe. The next episode is the image. In 2022, scientists released the first image of the black hole S2 has been orbiting for 30 years. The press called it a photograph. What none of them told you is what the image actually is. And when you understand that, the image becomes something else entirely. The star has been falling toward a black hole for 26,000 years. Humanity has only been watching it for 30. We know the physics of its destruction. We know the ending. What we do not know is whether that ending has already begun. The star has been falling for 26,000 years. We know it shouldn't exist where it is, and we know exactly how it ends.